Did you know that the sun survives by consuming itself every second, millions of tons at a time, and that life on Earth exists only because of this slow act of self-destruction? We see the sun every day. It rises on schedule, warms our skin, and fades into the horizon with reassuring familiarity. Over time, that familiarity has convinced us of something dangerous, that the sun is stable, gentle, and already understood. But this comfort is an illusion. In reality, the sun is a colossal energy engine, tearing itself apart at the subatomic level, converting mass into pure energy through processes violent beyond human intuition. It does not burn quietly. It does not rest. It roars continuously through magnetic storms, radiation, and forces powerful enough to dwarf every weapon our civilization has ever built. The only reason we don't hear this roar is because space itself is silent. What sustains Earth today is the same system capable of crippling our technology, disrupting our planet, and collapsing modern civilization within hours without warning. And without a single explosion, we live beside a star we believe we understand. Yet we've only begun to grasp how little we truly know. And once you understand what the sun really is, you will never look at a sunrise the same way again. The light that reaches you in the morning feels gentle enough to think of it as a greeting, as if the world is being quietly switched on again. It is easy to forget that what feels like a soft beginning is only the faint echo of something that has never been quiet, and never will be. From where we stand, the sun behaves like a metronome. It rises, it climbs, it sets. The pattern repeats so consistently that our nervous system has accepted it as background. Our language reflects that trust. Sunrise, golden hour, warm afternoon. None of those phrases carry danger. None of them hint at what it means to orbit an unshielded nuclear furnace. Part of the illusion comes from distance. The sun sits about 150 million kilometers away, far enough that all of its violence collapses into a flat circle in the sky. At that distance, the heat and light that reach us have already been filtered, spread, and softened by space itself. If you could somehow stand much closer without being destroyed, there would be no sense of a calm, glowing disk. You would find yourself inside a storm of radiation and charged particles so intense that the words weather or climate would stop meaning anything. Another part of the illusion comes from silence. On Earth, we associate danger with sound, thunder, explosions, the crack of something breaking. Our bodies are tuned to flinch at sudden noise, but space does not carry sound. The sun can release more energy in a moment than humanity uses in many years. And from here, it will always look like a steady light and feel like a warm day. Nothing screams. Nothing rattles the windows. The atmosphere translates that fury into a pleasant afternoon. At the level of physics, the sun is not calm at all. It is a ball of plasma, not gas in the way air is gas, but matter so hot that electrons and nuclei have been torn apart. In this state, it behaves less like something we can picture and more like a living ocean of charged particles, deeply tangled with magnetic fields. Those fields twist, snap, reconnect, and braid themselves through the plasma in ways that are still being mapped. What we see from Earth is only the averaged result of countless interactions we will never directly perceive. Every second, the sun is generating energy on a scale that does not fit inside human intuition. Its total power output is around 380 septillion watts. Written out in full, that is a 3, followed by 26 zeros. An amount so large that our usual comparisons collapse. One way to approach it is this. All of human civilization, every city, every factory, every data center and vehicle combined, consumes on the order of a few tens of trillions of watts. The sun emits more than 10 trillion times that, continuously, without a pause. To us, it becomes a nice day outside. Maybe fours. From the surface of the Earth, this power feels gentle only because we are intercepting a tiny fraction of it. Earth occupies a vanishingly small target in the sphere of space over which sunlight is spread. Only about 1/2 billionth of the sun's total energy output ever touches our planet. That is all we live on. Every forest, every ocean current, every heartbeat, and every server farm depends on that tiny slice of a star's output, diluted by distance. The rest of that power races outward into space, indifferent to whether any of it is used. The sunlight that lands on your skin is also old. In a strange way, once it escapes into space, it needs only about 8 minutes to travel from the sun to Earth. That part is swift, but before that journey, the energy was trapped inside the sun for an almost unimaginable length of time, absorbed and re-emitted by particles in the dense interior, wandering in a random walk that lasts tens of thousands of years. By the time it reaches you, the conditions under which it was created no longer exist. You are warmed by the aftermath of decisions the universe made long before any human eyes were here to see them. Even the surface that we think we are looking at is an illusion of stability. The layer we call the photosphere, the bright face of the sun, has a temperature of around 5,800 degrees Celsius. At that temperature, atoms are excited enough to emit the visible light we see. But what looks like a smooth circle from Earth is, up close, a boiling pattern of convection cells. Hot plasma rises, cools, and sinks again in a constant churning motion. Each bright granule is larger than many countries combined. Yet we only ever perceive the average effect, a uniform glow at a safe distance. Deeper inside, the calm disappears entirely. The core of the sun reaches temperatures around 15 million degrees Celsius, at pressures so high that hydrogen nuclei are forced close enough for quantum effects to allow fusion. This is not fire in any familiar sense. There is no flame, no fuel in the way we understand it, no air. There is only the relentless conversion of mass into energy, following rules that do not care whether anything alive is orbiting nearby. Human beings learned to name this process. We did not negotiate it, and we cannot turn it off. Silence, distance, and apparent regularity combine into a kind of cosmic camouflage. Because the sun rises every day, we treat it as reliable. Because it does not flicker visibly, we treat it as stable. Because we cannot hear it, we treat it as gentle. Our nervous system is built to handle immediate threats, a predator, a storm, a sudden fall. The sun does not behave like any of those things. It is too large, too constant, and too far away. It is a slow, continuous risk, and slow, continuous risks are the ones we are worst at taking seriously. This is where the unease begins to creep in. The sun does not need to do anything unusual to endanger us. Its normal behavior is already extreme. Slight variations in its activity can alter the space environment around Earth in ways that challenge our technology and infrastructure. Tiny fluctuations in energy output, variations so small that you could not feel them on your skin, can shift climate patterns over long timescales. For a star, these are minor adjustments. For a planetary civilization built on narrow assumptions, they are existential questions. There is a quiet asymmetry here. Every aspect of life on Earth depends on the sun. Our bodies evolved under its spectrum of light. Our sleep cycles track its rising and setting. Our agriculture, our energy systems, even our metaphors about hope and renewal lean on its presence. Yet the sun, as a physical object, remains completely untouched by whether we exist. It would shine almost exactly as it does now if Earth were a sterile rock. It will continue to shine long after our species has disappeared, whether we vanish through our own mistakes or through some external catastrophe. This indifference is not hostile. It is simply how physics works at this scale. The sun is not an enemy. It is also not a guardian. It is a process. And we are happening to exist inside the narrow envelope where that process makes complex chemistry possible on a small, rocky world. That envelope feels permanent only because our lives are short. Measured against the timescales of stellar evolution, every human era is a brief experiment being run under a particular set of conditions. Those conditions are set, ultimately, by a silent, continuous release of energy we tend to describe as nice weather. So, when you stand outside at midday and feel warmth on your face, it is tempting to treat that sensation as something personal, almost intimate, as if the universe were acknowledging you. The reality is colder and, in its own way, far more profound. The warmth is a trace amount of energy that has survived an enormous journey from the core of a star, through layers of plasma, through the vacuum of space, through the filter of Earth's atmosphere, and finally into the atoms of your skin. For a moment, those atoms vibrate a little faster. That is all. Yet on such transfers of energy, repeated countless times, entire lives are built. If this sounds unsettling, it is because it quietly undermines a story we tell ourselves, that the world around us is tuned to us, that what feels stable will remain stable because we have grown used to it. The sun is a reminder that stability, at cosmic scales, is often an illusion created by our limited lifespan and our limited senses. We have built our civilizations under the assumption that the light will always arrive on time, that the conditions we inherited are the conditions we are entitled to keep. The truth is less comforting. We live on a world that orbits a star whose full behavior we do not yet completely understand, whose internal dynamics are still being mapped by spacecraft and theory, whose future changes we can only model with incomplete confidence. We have turned its silence into reassurance, its distance into safety, and its regularity into a promise it has never made. The promise becomes thinner when you realize that the quiet circle you see is not actually where the real violence lives, that the most dangerous part of the sun is not what your eyes are drawn to, but what hangs just above it and almost disappears. Most of the time, when you look at the sun, you are not really seeing the sun. You are seeing only its photosphere, the bright, visible layer where light finally escapes after an almost unimaginable journey outward. That is the surface your childhood drawings tried to capture, a round disk, sometimes with rays, sometimes with a face. Above that apparent surface, there is something else. Something our senses barely register without help. A thin, ghostly atmosphere of superheated plasma called the corona, wrapping the star in a pale halo that stretches far into space. The corona should not exist in the way it does, not according to ordinary intuition. The photosphere glows at about 5,800 Kelvin, already more than hot enough to erase any everyday comparison. Yet above it, in the corona, the temperature leaps to values between roughly 1 million and 3 million Kelvin, sometimes higher in extreme events. The outer atmosphere is hundreds of times hotter than the surface it floats above. It is like holding your hand over a stove and finding that the air above the flame is far hotter than the flame itself, while the metal below remains comparatively cool. Physics does not usually behave like that. The fact that it does here is one of the great unresolved questions in solar science. For a long time, we did not even know this paradox existed. For most of human history, the corona revealed itself only during total solar eclipses, when the moon perfectly covers the photosphere and turns the sky dark enough for our eyes to notice the faint white crown around the blackened sun. For a brief few minutes, a filigree of light appears, delicate and structured, like hair blown outward by a wind we cannot feel. Then the bright surface returns, and the crown vanishes again into daylight. It is there all the time, but our senses are not built to notice it. Part of the reason is brightness. The corona is incredibly hot, but extremely tenuous. So thin that its visible light is only about 1/1,000,000th as intense as the light from the photosphere beneath it. To your eyes, the photosphere is overwhelming. It drowns out the dim halo above, the way a city's lights wash away the stars. The atmosphere that holds some of the sun's most explosive structures is effectively invisible to you unless something else blocks the glare. Or you build instruments that can filter it out. You grew up under a star whose most volatile layer you simply could not see. Today, satellites like the Solar Dynamics Observatory and the Solar Orbiter peel back that disguise. They do not look at the sun in ordinary light, but in extreme ultraviolet and X-ray wavelengths, where the corona shines more strongly. In those images, the sun is no longer a smooth golden disk. It becomes a tangled architecture of loops, arches, and streamers, tracing out the paths of magnetic fields that rise from the interior and punch through the surface. Those arcs glow because plasma trapped along them is heated to coronal temperatures, outlining invisible magnetic structures in luminous threads. To a human eye brought close enough, that region would not be calm. It would look like an enormous storm frozen in mid-motion. The paradox of the corona forces us to confront the limits of our intuition. We expect heat to flow outward and fade. Instead, something in the sun's upper atmosphere is adding energy. One family of ideas points to waves, magneto-hydrodynamic oscillations traveling upward from the turbulent layers below, dumping their energy in the tenuous outer atmosphere. Another focuses on countless small magnetic reconnection events, tiny, frequent explosions as field lines snap and realign, injecting heat into the plasma. Both processes may be involved. Neither has yet given us a final, simple answer. The star that makes life possible on Earth is still holding on to basic secrets about how it distributes its own energy. Viewed over time, the corona looks less like a decorative crown and more like a battlefield. Magnetic fields emerging from the sun's interior push into the atmosphere, twist together, and oppose each other. Where they become stressed, energy is stored like tension in a coiled spring. Where they realign, that tension is suddenly released, heating plasma, accelerating particles, and sometimes launching material outward into space. To a casual glance from Earth, none of this is visible. The disk still looks uniform. The sunrise still feels the same. Only the instruments notice that the star's outer atmosphere is constantly knotting and unknotting itself. There is something quietly uncomfortable in this difference between appearance and reality. We have built a story in which the sun is steady and soothing, a symbol of constancy. Yet, just above the visible surface is a region whose very temperature structure defies our expectations and whose behavior we cannot yet fully predict. We live our lives treating the sky as finished scenery, while the system that dominates our environment is still, in crucial ways, an open question. The corona also refuses to be small. It does not end a short distance above the surface, like the thin layer of air clinging to Earth. Instead, it extends outward for many solar radii, gradually thinning until it merges with the solar wind, a continuous flow of charged particles streaming through the solar system. The space between planets is not empty. It is filled with material that once belonged to the sun's atmosphere, shaped and accelerated by the same forces that heat the corona. Your planet is not orbiting outside the sun. In a physical sense, it travels inside the extended reach of its atmosphere. To understand that environment, we have begun sending instruments directly into it. NASA's Parker Solar Probe now flies repeated plunging orbits that carry it deep into the outer corona, approaching to within roughly 6 million kilometers of the visible solar surface. At that distance, the spacecraft is moving through the region where the solar wind is still forming, where the hot coronal plasma is transitioning into the streams that will eventually wash over Earth. It is the first human-made object to enter that realm directly. skimming the edge of a stellar atmosphere in a way that would have sounded like fiction not long ago. To survive, the probe carries a heat shield designed to endure temperatures of over 1,000 degrees Celsius, while keeping its instruments in a relatively mild shade. Seen from the spacecraft's frame of reference, the Sun is not a gentle circle, but an overwhelming source of radiation that fills much of the sky. With the corona stretching outward in all directions, it is as close as our technology has come to standing at the edge of a continuous explosion and trying to take notes. The data it sends back are not merely technical details. They are fragments of a larger answer to a question we did not think to ask until recently. What does it truly mean to live within the breathing space of a star? What the corona shows, more than anything, is that our sense of safety often rests on what we fail to perceive. From Earth, the sky seems empty and silent. In reality, the space around our planet is threaded with magnetic fields and filled with high-energy particles guided by structures rooted in the corona. Subtle changes in coronal conditions can ripple outward and shift the behavior of the solar wind at Earth's orbit, altering the shape of our planet's magnetic shield and driving currents in the upper atmosphere. The apparent calm above your head is a thin interface between your daily life and a dynamic environment shaped by forces on scales vast enough to ignore your existence entirely. There is a human tendency to believe that what we can see is what matters most. We trust the familiar surface, build our meanings around it, and forget that the deeper structure might be far stranger than our stories allow. The corona is a physical reminder that reality is not arranged around our comfort. The Sun does not tidy up its behavior to match our intuitions. It generates an atmosphere that is hotter than its surface, invisible to our unaided eyes, capable of storing and releasing energies we have only begun to model. And it does all of this without intent, without audience, simply because this is what happens when gravity, plasma, and magnetic fields interact under certain conditions. Standing on Earth, you are protected from most of this by distance, by a magnetic field, and by a layer of air only a few tens of kilometers thick. You do not feel the temperature jump in the corona. You do not feel the restructuring of magnetic fields thousands of kilometers above the photosphere. You feel instead the filtered warmth of sunlight on your skin, and you interpret that warmth as benign. But every gentle morning carries, hidden inside it, the imprint of a surrounding atmosphere that behaves more like a restless laboratory experiment than a stable background. If you let that fact settle for a moment, it shifts something subtle in the way you place yourself in the universe. You are not living under a ceiling that was designed to be safe. You are inhabiting a small, habitable pocket inside a much larger, more complicated system whose rules you did not write. The corona is not there for you. It is simply the shape that the Sun's outer layers take when energy and magnetism interact in this particular way. That shape happens, for now, to allow a rocky planet at a certain distance to host liquid water, complex chemistry, and minds capable of wondering why the outer atmosphere of their star is hotter than its surface. It is easy to treat that as a satisfying puzzle, one more problem for science to solve. But there is another dimension to it. The unresolved physics of the corona, the heating mechanisms we are still debating, the structures we are still mapping, all point to a deeper truth. The environment that sustains us is not fully understood. Even now, you wake up each day under a star whose outer layers still contain open questions. And yet every plan you make quietly assumes that its behavior will remain within a narrow, favorable range. The paradox does not end at the edge of the Sun. It extends into the way we live, confident inside a system we have only partially deciphered. Sometimes that incomplete understanding is quietly harmless, but not always. There are moments when the hidden structure of the corona stops being abstract and throws matter and energy across space in ways that reach us directly. Those moments are solar flares and coronal mass ejections. and they are the closest thing our star has to an outburst. They do not look like eruptions from the ground. You do not see anything leap off the sun with your unaided eyes. A flare appears, invisible light, as a brief brightening near a sunspot group. In other wavelengths, it is far less modest, a sudden release of energy from stressed magnetic fields in the corona, heating plasma, accelerating particles, and flooding space with radiation across the spectrum. A large solar flare can release up to roughly 10 to the power of 25 joules of energy, comparable to millions of major volcanic eruptions on Earth compressed into a single event that lasts from a few minutes to a few hours. It is difficult to map that onto human experience. We sometimes call nuclear weapons unimaginable. Yet, even the most powerful devices humanity has ever tested are tiny beside such an event, like sparks beside a lightning bolt. For the Sun, these flares are local rearrangements of its magnetic architecture, intense but geographically small compared to its vast surface. For us, at the receiving end of their radiation and particles, they are reminders that our orbit lies within range of more than just gentle light. Solar flares are rooted in complexity. In active regions where magnetic fields are especially strong and tangled, energy accumulates as fields are twisted and sheared by the motion of plasma below. Eventually, the configuration becomes unstable. Field lines break and reconnect in new patterns, a process known as magnetic reconnection. In that instant, stored magnetic energy is converted into heat, kinetic energy, and radiation. Particles are hurled to near-relativistic speeds. X-rays and gamma rays flare into existence. To an instrument in orbit, the Sun suddenly brightens in high-energy wavelengths. Then, over minutes to hours, the intensity fades again. The star resumes its apparent calm. Sometimes, these magnetic rearrangements do more than brighten a patch of corona. They can also launch a coronal mass ejection, a vast bubble of plasma and magnetic field that detaches from the Sun and moves into interplanetary space. A single coronal mass ejection can carry a mass on the order of around 10 to the power of 12 to 10 to the power of 13 kilograms of solar material, embedded in its own twisted magnetic field. That is not an abstract quantity. If you tried to imagine that much matter as water, it would be more than enough to fill all of Earth's oceans many times over, lifted up from the Sun's atmosphere and thrown outward. The speeds involved are just as unsettling. Typical coronal mass ejections travel at a few hundred kilometers per second, fast enough to cross the distance from Earth's surface to geostationary orbit in well under a minute. If they maintain that speed starting from here, the fastest recorded events can reach or exceed about 1,000 to 1,500 kilometers per second, and in rare cases, even higher. At those speeds, an ejection aimed toward our planet can traverse the distance from the Sun in as little as something like 15 to 18 hours, or it may take several days if slower. Either way, the timescale is not geological. It is not even historical. It is human. The gap between a quiet afternoon and the next morning's news. There is a particular unease in knowing that such events are not rare mistakes. But part of the Sun's normal behavior, coronal mass ejections become more frequent around the peak of the solar cycle. When the Sun's magnetic field is more tangled and active, near solar maximum, the star can produce on the order of several ejections per day. Near solar minimum, the pace slows to roughly one every few days. It is a breathing rhythm on an 11-year scale, and Earth happens to orbit inside the space where those breaths sometimes pass. What makes this especially relevant to us is not simply that flares and ejections occur, but that they sometimes align with our planet. Most of them do not. Coronal mass ejections expand outward in all directions. Only a small fraction are aimed in just the right way to intersect Earth's orbit at the right time. When they do, the cloud of plasma and magnetic field collides with our planet's own magnetic bubble, the magnetosphere. The encounter compresses the day side, stretches the night side into a longer tail, and triggers waves of reconnection and energy release that we call geomagnetic storms. To a satellite in orbit, this is not theoretical. Increased particle flux can damage electronics, degrade solar panels, and interfere with communication and navigation signals. In the upper atmosphere, heating and expansion can increase drag on low Earth orbit satellites, subtly altering their paths. On the ground, rapid changes in the geomagnetic field can induce currents in long conductors like power lines and pipelines under the wrong conditions that can overload transformers and disrupt electrical grids across large regions. None of this requires the sun to do anything unusual. It only requires an eruption of the kind it has produced many times, directed just slightly more toward us than usual. History has already given us a preview. In the year 1859, a powerful storm, now known as the Carrington event, struck Earth. It was associated with an intense flare observed by Richard Carrington and Richard Hodgson, and likely with a coronal mass ejection that reached Earth in an unusually short time. The resulting geomagnetic disturbance caused auroras visible close to the equator and induced currents that set telegraph equipment on fire and shocked operators through their hands on the keys. At that time, the global electrical infrastructure was limited to telegraph lines. Today, our dependence on electricity and satellite technology is woven through every part of daily life. In a sense, the Carrington storm arrived early, in a world not yet capable of being fully harmed by it. It is possible that equally strong or stronger events have occurred in centuries before, when there were no technological systems sensitive enough to record their full impact. When we look at ice cores and tree rings, we can sometimes see chemical signatures of past particle events, hints that the sun has, on occasion, sent fluxes of energetic particles far above the usual background. We do not know exactly how often such extremes occur. We only know that our species has chosen to build a civilization whose critical functions can be affected by them. From a distance, this might sound like a story about risk management and infrastructure resilience. It is that, but it is also something deeper. Solar flares and coronal mass ejections are physical manifestations of a more general truth. We exist inside a system that can, without malice, briefly rearrange the conditions under which our plans make sense. The sun does not need to target us. It does not even notice us. Its magnetic fields evolve. Energy is stored and released. Plasma is accelerated and thrown outward. If one of those ejections happens to intersect the orbit of a small inhabited planet, the consequences unfold, according to electrical and magnetic laws that were in place long before there were power grids to overload. Standing on the surface, under a clear sky, nothing in your senses tells you when such an eruption has occurred. You cannot hear the flare. You cannot see the coronal mass ejection with your eyes alone. Somewhere on the sun, a brightening in X-rays has started and faded. A magnetic structure has destabilized and thrown a cloud of plasma outward. And you feel only the same warmth on your skin. The gap between cause and perception is filled by satellites, instruments, and models, technological extensions of our senses that watch the sun continuously because our bodies never evolved the ability to do so. Those instruments also confront us with a strange asymmetry in time. A flare begins and ends on the sun in a matter of minutes to hours. The light from that flare reaches Earth in roughly 8 minutes. The associated coronal mass ejection, if present, may not arrive for many hours or several days. We live in that interval, in the waiting space between seeing an event and experiencing its full effects. It is a reminder that even with modern monitoring, our relationship to our star is not one of control. It is one of awareness, preparation, and acceptance that some variables lie outside our direct reach. If you zoom in further on what happens during a flare, the disparity between human and stellar scales becomes even more stark. During the impulsive phase of a large flare, electrons and protons can be accelerated to energies of millions of electron volts. high enough that a single particle can penetrate spacecraft shielding or, in rare cases, pose a radiation hazard to astronauts outside strong protective fields. These are not abstract numbers. They are reminders that the space just outside our atmosphere is not a neutral void, but a region whose conditions are influenced by eruptions on the sun in ways that can challenge human tissue and technology alike. And yet, for all their power, flares and coronal mass ejections are still small perturbations compared to the star's overall output. A flare releasing up to around 10 to the power of 32 ergs, or about 10 to the power of 25 joules, is still delivering less energy than the sun radiates in all directions in a single second. From the star's perspective, these events are localized adjustments, small rearrangements of its magnetic field. From ours, they are large enough to knock out communication systems, damage satellites, and push auroras far closer to the equator than usual. The same event is trivial at one scale and overwhelming at another. There is a quiet philosophical pressure here. It is one thing to know, in theory, that the universe does not scale itself to human concerns. It is another to trace that indifference into the specific behavior of something you rely on every moment. Solar flares and coronal mass ejections are not stories from distant galaxies or early cosmic epochs. They happen on the star that sets your daily rhythm, whose light defines your sense of day and night. They are disruptions in the very system you unconsciously treat as background. From an existential point of view, they reveal a particular kind of vulnerability. Human life depends on a narrow band of conditions, a stable range of temperatures, predictable cycles of light and dark, electrical infrastructures that function within certain tolerances. Coronal events do not target those conditions, but they can push them, briefly, out of their usual range. A powerful enough storm could, in principle, leave large regions without power for weeks or months, severing the technological bonds that many of us now mistake for the fabric of society itself. In that gap, between what we assume is permanent and what is merely ongoing, our real dependence is exposed. None of this means we are helpless. We can monitor the sun, forecast space weather, harden our systems, design power grids and satellites with storms in mind, and plan for recovery. But even these measures have a subtext. They are acts of adaptation to a larger process, not acts of mastery over it. We are learning to live with a neighbor we cannot move away from, whose moods we did not cause and cannot fully predict. When you hear the phrase solar storm, it is easy to imagine something noisy and cinematic. The reality is stranger, a burst of radiation arriving silently at the speed of light, followed hours or days later by a moving structure of plasma and magnetic field that your eyes will never see. Electronics will register it. Magnetometers will trace it. High-latitude skies may glow. Power engineers may watch their systems with unease. And somewhere in all of that, you will still wake up, step outside, feel the familiar warmth on your face, and perhaps never realize that, in the space above you, your planet has just passed through the debris of a soundless explosion on the surface of its only star. The soundless explosions matter when they reach us, but most of the time the sun's violence does something quieter. It rises, falls, and exhales into space in long, slow motions that almost never touch our awareness. From a distance, the sun looks like a perfect sphere. In reality, it is constantly throwing parts of itself upward and then pulling them back down, like a hand lifting water only to let it fall through its fingers. One of the most striking examples of this is what solar physicists call coronal rain. High in the corona, plasma can cool and condense along magnetic loops, forming droplets and streams that begin to fall back toward the surface under the pull of gravity. To an instrument watching in extreme ultraviolet light, These are not gentle drizzles but bright strands and clumps sliding along invisible rails, sometimes reaching speeds of up to around 150 kilometers per second before they vanish into the lower atmosphere. Nothing about that feels like the word rain as we use it on Earth, except the basic pattern. Something lifted up, something that cannot stay, something that must return. The corona is so hot and tenuous that it should be hostile to condensation. Yet, under the right conditions, heat is lost faster than it is supplied, and plasma makes the improbable transition from diffuse to clumped. In those moments, the sun is briefly full of downward motion. Streams of matter that a few hours earlier were part of the faint outer atmosphere and now fall back toward the photosphere along curved paths defined by magnetic fields. These loops themselves are enormous. Solar prominences, which often host coronal rain, can arch hundreds of thousands of kilometers above the surface, towering far higher than any human scale. A typical large prominence extends for many tens of thousands of kilometers. The largest prominence on record stretched more than 800,000 kilometers into the corona, roughly comparable to the radius of the Sun itself. One particularly famous granddaddy prominence, photographed in the mid-20th century, rose to around 200,000 kilometers and erupted with a speed of about 200 kilometers per second. Against that scale, Earth shrinks to a detail, a small sphere that could be tucked comfortably under one arch of plasma and forgotten. Prominences do not flash into existence and vanish instantly. They can take on the order of a day to form, gradually building up as plasma collects along magnetic structures, and some remain stable for weeks or even months, hanging over the solar limb like suspended rivers. Within them, temperatures are cooler than the surrounding corona, densities higher, and flows more organized. Over time, segments of these structures cool further, detach, and fall as coronal rain, sometimes in repeated cycles of condensation and descent. From our vantage point, it is as if the sun were learning and relearning the same motion, lifting, holding, and then letting go. There is a quiet irony in this. We often imagine stars as symbols of permanence. Yet here is a process that looks almost domestic in its repetition. The sun hoists material upward along magnetic loops, only to let gravity reclaim it. Nothing is really preserved. The prominence that seems so stable when captured in a still image is, in fact, a transient form, built from plasma that is always moving, always changing, always on its way somewhere else. If you could somehow anchor your point of view and watch a single region for months, you would see structures appear, swell, drip, and disappear, while the underlying star remains indifferent to any of them. Not all of the plasma that rises into the corona falls back. Some of it finds another path outward, one that does not return at all. The sun is constantly streaming material into space as the solar wind, a flow of charged particles that escapes the corona and fills the solar system. This wind is not uniform. In some regions, especially near what we call coronal holes, areas where the sun's magnetic field opens out into space rather than looping back, the plasma can accelerate to high speeds. Observations from missions such as Ulysses and others have shown that slow solar wind typically moves at around 400 kilometers per second, while fast solar wind can reach speeds of about 800 kilometers per second. These numbers are easy to recite and impossible to feel. A parcel of fast solar wind leaving the sun would cover the distance from the sun to Earth, one astronomical unit, in only a few days. There is no way for your body to know this. On the ground, the sky looks the same, yet above you, every moment, streams of plasma are sweeping past, guided by the sun's magnetic geometry. Shaped by structures in the corona you will never see directly. Your planet is not parked in empty space. It is moving inside a continuous exhalation. The cost of that exhalation is real. Each second, the solar wind carries away mass from the sun itself. Estimates place the mass loss at roughly between 1,300,000 and 1,900,000 tons every second. A flow so large that, over time, it adds up to a mass comparable to Earth, roughly every 150 million years, over the entire lifetime of the Sun so far. This has changed its total mass by only a tiny fraction of a percent. Not enough to alter its basic identity, but it is a reminder that even stars do not keep all of themselves. They are always, in some sense, thinning. Coronal holes, the regions that help feed the faster components of the solar wind, appear in extreme ultraviolet and X-ray images as dark patches, not because they are cold, but because the plasma there is less dense and the open magnetic field lines allow material to escape more readily into space. They are like missing pieces in the luminous crown, windows where the Sun's atmosphere does not close back on itself. When those open field regions rotate into alignment with Earth, the enhanced outflow can sweep past our planet, disturbing its magnetic environment and sometimes driving geomagnetic activity even without a dramatic flare or coronal mass ejection. Seen as patterns, these processes give the Sun something like a rhythm of breathing. Plasma is heated, lifted, and accelerated outward along open field lines, forming the solar wind. Elsewhere, plasma rises into closed loops, cools, condenses, and falls back as coronal rain. Prominences rise and hang, as if held in the star's extended hand, before breaking apart or being launched into space. Each motion obeys the same underlying fields and flows, but the outcomes differ. Some material returns, some circulates, some is lost forever. If you strip away the imagery, what remains is a network of exchanges. The corona is not a static shell, but a stage on which energy and matter are constantly being redistributed. The Sun's rain and breath are two faces of that redistribution, where we see arches of glowing plasma and streams of outward flow. The underlying reality is magnetic topology changing shape, waves carrying energy, and particles responding. Humanity enters this picture only as a late consequence, at one small distance from the star, under one particular combination of flows and fields. Conditions happen to allow for a world with liquid water and complicated chemistry. It is tempting to turn that into a story about balance, as if the Sun were carefully tuning its rain and its breath to keep our orbit comfortable. The physics does not support that. The rates of mass loss in the solar wind, the sizes and lifetimes of prominences, the occurrence of coronal rain, none of these processes are adjusted for us. They are set by the interplay of gravity, rotation, magnetic fields, and plasma dynamics. For billions of years, those interactions have created an environment in which Earth can exist as it does. At some point in the future, they will shift enough that our familiar conditions will no longer hold. At human timescales, though, what we see is persistence. The same kinds of structures recur, the same patterns of rising and falling, the same outflow of solar wind. Observatories watch the Sun banded with prominences, threaded with coronal rain, ringed with coronal holes. And the longer they watch, the clearer it becomes that nothing truly stands still. The things that look solid in a single image are in motion when you watch them as a film. The things that look permanent across a lifetime are transient when you measure them against stellar evolution. There is a quiet lesson in that. On Earth, we often mistake recurrence for permanence, the way waves keep reaching the shore, the way seasons cycle, the way the Sun climbs and falls along the horizon. In the corona, those recurrences are simply the visible face of deeper flows that have no obligation to remain exactly as they are. The Sun's rain and breath remind us that even at the scale of a star, stability is a kind of average, not a promise. And yet, for now, that average holds. The solar wind continues to stream outward, thin enough that it has taken space missions and delicate instruments to measure it, strong enough that it shapes the entire magnetic environment of the solar system. Prominences keep arching out of the photosphere into the corona, sometimes erupting, sometimes collapsing, sometimes quietly returning their mass to lower layers. Coronal rain keeps falling along invisible tracks, a star's own weather, witnessed from 93 million miles away and only understood because a small species built eyes that could see beyond visible light. When you look up at the sky in daylight, none of this announces itself. You see brightness. You feel warmth. Somewhere above that blue, the sun is at that moment lifting part of itself into space, breathing particles into the void and pulling other fragments back down in shining streams. You live, unknowingly, inside the region where that breathing happens to be thin enough and that rain happens to fall far enough away that a fragile biosphere can emerge and ask what it means to exist inside the circulation of a star. If you follow that question all the way back toward the sun itself, you eventually reach a place where its breathing becomes something more abrupt, where the gentle idea of a star's atmosphere gives way to a cliff in temperature so sharp that our normal understanding of heat simply fails. Between the chromosphere and the corona, there is a layer so thin that, by solar standards, it is almost nothing. And yet within that short vertical distance, the temperature of the sun's atmosphere rises more violently than anywhere else we know. This is the transition region, above the chromosphere, over a thickness of only about 100 kilometers. The gas jumps from roughly 20,000 degrees Kelvin to more than 2 million degrees Kelvin. It is as if you could stand on a hillside and walk from a cool evening into the heart of a furnace in a few steps. And the furnace itself would not bother to explain why. On Earth, when we heat something, we expect the rules to be simple. Add energy, the temperature rises. Remove energy, it falls. In the sun's transition region, that logic breaks. Here, a small change in heating produces a disproportionate effect, slightly more energy, and atoms lose additional electrons, changing the way they radiate. Helium becomes fully ionized. Radiation becomes less efficient at carrying energy away, and the gas suddenly jumps toward coronal temperatures. Slightly less energy, and the opposite happens. The material cools rapidly toward tens of thousands of degrees Kelvin again. Solar physicists sometimes describe this as a kind of temperature catastrophe, a phase transition in which the atmosphere flips between very different states with only modest changes in input. The transition region is not a smooth, uniform shell. It is more like a ragged boundary woven through with loops, jets, and shocks. Below it, in the chromosphere, gravity and gas pressure still play a strong role in shaping structures. Above it, in the corona, magnetic forces dominate the motion of plasma. In between, the usual simplifications break down. The gas is partly ionized. Radiation and particles are out of equilibrium with each other. And the scales of time, distance, and density all conspire to defeat easy modeling. Hydrogen, the sun's main ingredient, refuses to behave in a tidy way here. In the upper chromosphere and lower transition region, the density is too low for the ionization state of hydrogen to track the local temperature instantly. The timescales over which hydrogen atoms gain or lose electrons can be longer than the timescales over which shocks and waves pass through the gas. So the plasma is often out of statistical equilibrium. In practical terms, this means that if you try to describe the state of the gas using the same rules that work for a laboratory flame or a hot oven, your description will be wrong. You cannot simply say, at this temperature, hydrogen is this ionized. You have to follow the history of the gas, the path it took to reach its current state. This is one of the reasons the transition region feels like a place where physics breaks, even though it is still obeying the same fundamental laws. The laws themselves have not changed, It is our approximations that fail. For decades, models of the solar atmosphere treated layers as neat, horizontal slabs. The transition region revealed that approach as wishful thinking. This boundary is highly structured, threaded by magnetic fields that rise and fall, and pierced by jets of plasma that ignore any idea of a simple, flat surface. Spicules are among the most striking of those jets. Seen at the solar limb in suitable wavelengths, they look like thin, grass-like spikes shooting upward from the chromosphere into the transition region and beyond. Their typical diameters are on the order of about 1,000 kilometers, and they become visible only above roughly 5,000 kilometers over the limb. Many of them race upward at speeds of tens of kilometers per second, with some types reaching velocities between about 80 and 300 kilometers per second before fading. Their lifetimes are brief, often only a few minutes from rise to disappearance. To an instrument, the transition region is full of such transients, a forest of jets constantly punching through the boundary between cooler and hotter layers. Recent observations suggest that many spicules are heated to near coronal temperatures as they rise, carrying energy and mass upward and helping to feed both the corona and the solar wind. In some cases, their emission in certain ultraviolet lines can brighten to several times the background, signaling that the material has reached around 1 million degrees Kelvin or more. What looks, in early images, like a thin gray fringe at the limb is, under higher resolution, a dynamic conveyor belt moving mass, energy, and magnetic structure upward through the very region where our intuition about temperature fails. All of this is happening over a height compared to which a medium-sized terrestrial mountain range would be a microscopic wrinkle. Above the photosphere, the chromosphere extends for perhaps a few thousand kilometers, with temperatures rising from something like a few thousand degrees Kelvin at its base to tens of thousands of degrees Kelvin at its top. Then, in that thin transition region of roughly 100 kilometers thickness, the temperature leaps again toward the million-degree range of the corona. Compared to the sun's overall radius, hundreds of thousands of kilometers, this layer is a razor's edge. Yet it is on this edge that the star decides whether its outer atmosphere will be hot and extended or cooler and more compact. There is something conceptually unsettling about that. Entire models of stellar behavior depend on what happens in this narrow region, and yet it is so small that if you could shrink the sun to the size of a large globe in a room, the transition region would be thinner than a coat of paint. You live on a planet whose climate, space environment, and radiation conditions are influenced by processes that unfold in a layer you could not see, could not stand in, and cannot yet simulate with full confidence. In the transition region, different forces, trade dominance, below, gas pressure can still push structures around, and gravity helps define layers. Above, magnetic tension and pressure become more important, shaping loops and guiding flows. Within this boundary, neither description is quite enough. Plasma is dragged and twisted by magnetic fields, but the gas also responds to shocks, waves, and radiative losses in ways that are hard to disentangle. If you try to ignore magnetism, the models fail. If you try to ignore the gas dynamics, they fail differently. The sun, in this region, refuses to be simple. From an existential angle, the transition region is a quiet reminder that the universe does not have to be intuitively legible to the creatures living inside it. We evolved on the surface of a small planet, with senses tuned to the slow changes of air, water, and rock. We did not grow up inside a plasma at 100,000 degrees Kelvin, threaded by magnetic fields and out of equilibrium with itself. When we look outward, it is natural to expect that the sky will behave like an extension of the familiar. The transition region simply does not care about that expectation. It is a set of conditions under which the same physical laws produce behavior that feels almost alien. And yet, the consequences reach us in ways that are very human. The efficiency with which the transition region transports energy into the corona influences how much mass escapes as solar wind, which in turn affects the shape of the heliosphere, the giant magnetic bubble that shields the solar system from some incoming cosmic rays. The density and temperature structure of this layer help determine how the corona looks, how it stores and releases energy, how easily material can be accelerated outward. When we send spacecraft to other planets or astronauts beyond low Earth orbit, their radiation environment is shaped partly by decisions made without intention. In this narrow atmospheric boundary, in a way, the transition region is a crossroads. Energy rising from below can be radiated away, trapped, or allowed to move upward more efficiently. Matter can be kept close to the star, or helped along on its path into interplanetary space. Neutral atoms become ions. Ions recombine. Spectral lines that we observe as bright or dark features are written there, encoding the state of the plasma in patterns of ultraviolet light. Everything that happens in that space is, at its core, just particles and fields interacting. But when you are the descendant of organisms that depended on long periods of relative environmental stability, it is hard not to see these interactions as part of the precarious precondition for your own existence. If you could somehow stand in the transition region, you would not last. But imagine, for a moment, that you could witness it without being destroyed. You would see a landscape that is not really a landscape, filaments and jets shooting upward, fading, and being replaced, shock waves propagating through partially ionized gas, narrow layers where the temperature and density change over distances smaller than a typical terrestrial storm cloud. The idea of up and down would blur, replaced by directions defined by magnetic field lines. Time would feel different, measured in lifetimes of spicules and oscillations of waves rather than in hours. From Earth, all of this is compressed into a single word, atmosphere, and a single impression, the sun. The rupture between what is happening and what we perceive could not be wider. The transition region is a knife edge we never see, a place where energy, matter, and radiation renegotiate their relationship in ways that make our kind of sky possible. We pass our days under that sky, making plans as if the world were built on something solid, while above us, in a layer thinner than any map could meaningfully draw, the star that sustains us is busy breaking our simple ideas of how heat should behave. The knife edge you never see is also the floor you think you are standing on. The place where your idea of a surface begins is, for the sun, just another thin, unstable layer in motion. What we call the photosphere is not a crust or a solid skin. It is a relatively thin layer of gas where the sun finally becomes transparent enough for light to escape into space. Its average temperature is about 5,800 Kelvin, cool only in comparison with what lies below, and hot enough that atoms are constantly colliding, emitting the continuous spectrum we recognize as sunlight. If you could stand at a safe distance with impossible eyes, the photosphere would not look like a clean, featureless disk. It would look like a restless sea. Across this layer, convection from below breaks the surface into a pattern called granulation. Hot plasma rises in bright cells, cools as it radiates energy, and then sinks back down along darker lanes. Each granule is roughly 1,000 kilometers across, on the scale of a small country. Yet from Earth they blur into a vague mottling unless you use powerful instruments. The vertical motions inside these cells are fast by any human comparison, on average about 2 kilometers per second, sometimes reaching several times that speed. Flows so rapid that they are supersonic in the thin solar gas. The most unsettling detail is their lifespan. Each granule survives for only around 20 minutes before it breaks apart and is replaced by others. In that time, hot material has risen, cooled, and sunk again, giving up its energy to the light we see. The photosphere is completely resurfaced, cell by cell, over and over. What looks, at a human glance, like a permanent face is built from structures that appear and disappear faster than a short meeting. If you could watch the sun up close in accelerated time, you would see the photosphere boiling, erupting, and rearranging itself without pause. Even this granulation sits inside larger patterns. Supergranulation, a more extensive flow pattern, organizes the photosphere into cells roughly tens of thousands of kilometers in diameter, with horizontal flows of a few hundred meters per second and lifetimes on the order of a day. These giant cells herd smaller granules, sweep magnetic fields toward their boundaries, and shape the network of bright points and dark lanes that form the photospheric background. The surface is not just churning, it is churning in layers, with different scales of motion superimposed like overlapping currents in a turbulent ocean. The thickness of the photosphere itself is surprisingly small. From its bottom to its top spans only a few hundred kilometers, a distance negligible compared with the sun's radius of hundreds of thousands of kilometers. Within that narrow band, the temperature drops from roughly 6,600 Kelvin at the base to about 4,400 Kelvin at the top. Enough contrast that different spectral lines form at different depths, letting us probe the physics of a layer that, to the eye, seems simply bright. When you look at the sun, you are not seeing into it. You are seeing through a shallow fog of incandescent gas, thin in extent, thick in intensity. We habitually talk about the surface of the sun as if it were analogous to ground beneath our feet. But the photosphere is more like the visible crest of a much deeper convective system. Below it, rising and sinking flows carry energy outward from the interior. Above it, radiation escapes more freely, and the gas becomes part of the chromosphere and corona. The photosphere is the place where the balance tips, where matter stops, effectively trapping light, and starts letting it go. There is nothing special about this layer in terms of composition. Its importance comes from optical depth, from the way its density and temperature conspire to let photons finally travel unimpeded. Within this restless skin, magnetic fields carve out their own patterns. In some regions, fields become so strong that they inhibit convection, blocking the normal upwelling of hot plasma. Where that happens, the surface cools relative to its surroundings, and dark patches called sunspots appear. The umbra, the darkest central part of a typical sunspot, can have a temperature of around 4,300 Kelvin, with the surrounding penumbra somewhat hotter but still cooler than the average photosphere. The contrast makes them stand out as blemishes on the bright disk. But those blemishes are only the visible marks of magnetic structures that extend far above and below what you can see. The field strengths involved are far beyond everyday experience. Measurements show that magnetic fields in sunspots often reach several tenths of a Tesla, hundreds or thousands of times stronger than the average solar background field and thousands of times stronger than Earth's natural field at its surface. That concentration of magnetic energy is what ties sunspots to flares and coronal mass ejections. They are the anchor points, the places where field lines pierce the photosphere and connect to the tangled architecture above. When you see a sunspot, you are seeing the foot of a magnetic structure that may shape events in the corona days later. From an existential angle, there is a particular discomfort in the way the photosphere hides and reveals. It is the only part of the sun we can see in ordinary light. So our minds instinctively treat it as the star's identity, this bright circle, this color, this apparent stability. But everything we call surface detail is the manifestation of processes that are both far larger and far shorter lived than our senses can appreciate. Granules, supergranules, and sunspots are not decorations on a stable object. They are the object, as much as anything we might want to call the true sun underneath. That distance between perception and reality should feel familiar. Human beings also tend to treat the most visible layer of their lives as the most solid, the routines, the cities, the digital surfaces they touch. Underneath, just as in the photosphere, are flows and fields they barely register, slow shifts in climate, economy, technology, and biology. The solar surface is a reminder that what presents itself as a smooth face can be a high-resolution blur of constant change. We draw a line, call it a boundary, and build our meanings on the assumption that what sits beneath it does not matter day to day. The sun quietly demonstrates that the boundary is only where our vision happens to saturate. The photosphere is also where the sun turns into an object of sound, at least indirectly. The same convective motions that create granules launch acoustic waves into the interior. Those waves reflect, interfere, and set the star ringing with millions of simultaneous oscillations. Helioseismology, the study of those ripples, allows us to infer the internal structure and rotation of the sun. Much as seismologists use earthquakes to probe Earth's interior, the surface that looks still to your eye is, in fact, pulsating very slightly in complex patterns. A resonant drumhead whose vibrations carry information from far below. Seen this way, the photosphere is not a mask hiding the sun's interior so much as an interface through which the interior speaks. Temperature variations, brightness patterns, Doppler shifts from rising and falling gas, and magnetic signatures all carry messages about zones we cannot see directly. Spacecraft and observatories are, in a sense, elaborate listening devices pressed against a star's skin when they report that the granules are moving faster in one region or that a new sunspot group has rotated into view. They are hearing something change in the deep plasma beneath, translated into surface motion. At human scale, there is an instinctive desire for something firm underfoot, some foundation that does not move. The photosphere offers no such reassurance. It is a boundary defined by optical depth, shredding and reforming itself constantly. Yet this unstable layer is what gives you every sunrise you have ever seen. The light that makes a landscape look warm, that outlines a face at a window, that throws long evening shadows, has last touched matter in this shifting sea of convection and magnetism. You live your entire life by the rhythm of something that never stands still for even a single moment. If you could watch the sun continuously for centuries, the pattern would repeat and still never truly repeat. Granulation would churn on timescales of minutes, supergranulation on days, sunspot cycles on years, and deeper changes over far longer spans. The surface would age and renew, just as any living world does. Except that here the world is a star. From one human lifetime, the disk looks constant enough that we weave it into our symbols of reliability. From the perspective of the physics involved, constancy is an illusion built from countless individually unstable processes. This is the quiet message written on the photosphere, that what feels stable can be a moving average, that what looks serene can be the visible tip of restless energy, and that what we treat as a backdrop is, in fact, a system with its own changing structure. Every time you glance at the sun as light reflected from a wall, as a glow on water, as a muted disk behind thin cloud, you are reading a momentary state of a layer only a few hundred kilometers thick, flickering with convection cells larger than continents, threaded with magnetic fields strong enough to reshape space around your planet. And in that realization, the familiar star above you shifts slightly in character. It is no longer a simple lamp or a symbol of constancy. It is a surface of boiling gas that never keeps the same pattern, whose brief structures and deep flows together sustain the conditions for your existence. You stand under that changing skin and call it day. We've retooled the self. The surface that rules your days is just a temporary skin on something much older and stranger. To feel how provisional that comfort really is, you have to imagine a time when there was no sun at all, and no sky for it to rise into. Long before there was a star here, there was only a cloud, not a neat, bright nebula from a textbook, but a cold, lumpy giant of gas and dust drifting in the galaxy's spiral arm. Astronomers call these giant molecular clouds. Some of them can be roughly 1,000,000 times more massive than the Sun and stretch for around 150 light-years across. Dark against the background because their dust blocks starlight instead of reflecting it. Inside that darkness, hydrogen sits mostly as molecules, chilled to just a handful of degrees above absolute zero, waiting in no particular hurry. Gravity begins quietly, a slightly denser pocket forms, perhaps nudged by a passing spiral arm, the shockwave of a distant supernova, or the combined tug of nearby stars. That patch of cloud, only marginally heavier than its surroundings, starts to collapse under its own weight. At first, nothing about it would register to an eye that could see the whole cloud. The change is only in the balance between pressure pushing outward and gravity pulling inward. And for a long time, the difference is subtle. Then, as material piles in, the center grows denser, and the collapse accelerates. What will eventually become the Sun starts its life as one of these collapsing clumps, still buried in the opaque cloud. Gas falls inward, its potential energy converted to heat, and a central object takes shape, a protostar, not yet hot enough for nuclear fusion but already luminous from contraction alone. At this stage, the forming Sun would be larger in radius than it is now, cooler at the surface, and surrounded by an envelope of infalling matter. Most of its light is trapped and reprocessed by dust to an outside observer at visible wavelengths. It would be almost invisible. Around this growing core, angular momentum refuses to vanish. The collapsing material cannot fall straight in. It has some initial spin, and as it contracts, that spin speeds up. The result is a disk of gas and dust orbiting the young star, flattened by rotation. In that disk, grains collide and stick, building larger aggregates, then kilometer-scale planetesimals, and eventually the cores of planets. None of this requires a plan. It is the natural outcome of gravity acting on a slightly rotating cloud, plus the tendency of matter to clump when given time and collisions. Inside the protostar, the story is slower. As gas continues to fall in, the central temperature and pressure rise. The object shines by releasing gravitational energy, not by fusion. And for a long time, that is enough to hold up its own weight. The time spent in this pre-main sequence contraction phase is not short. Calculations and models suggest that a star of roughly solar mass spends on the order of tens of millions of years contracting before its core conditions cross the threshold for sustained hydrogen fusion. For our Sun, that journey from collapsing clump to stable main sequence star likely took roughly 50 million years. During that entire span, there is no single instant you could point to and say, "Here the star is born." Fusion reactions begin gradually, first in small amounts, then more steadily, while contraction slows as internal pressure rises. At some point, the energy produced by fusion in the core balances the energy radiated from the surface, and the star settles into a quasi-stable state. But this balance is not an event. It is the crossing of a threshold defined by continuously changing conditions. The narratives we like birthdays. First steps. Clear beginnings fit poorly here. The Sun did not switch on. It arrived. The cloud that gave birth to it was itself not pristine. The gas and dust in giant molecular clouds carry the chemical fingerprints of previous stars, heavier elements forged in earlier generations, and spread by supernovae and stellar winds. The carbon in your body, the oxygen in your lungs, the calcium in your bones, all existed in that cloud before the Sun did, assembled in the cores and explosions of stars that lived and died long before this region of the galaxy hosted a planetary system. Star formation is not a clean beginning. It is recycling at a scale that makes individual lifetimes seem almost decorative. As the protosun contracted, it passed through phases we can only reconstruct from theory and by observing other young stars. At first, it was swaddled in the cloud, visible, mainly in infrared, as a warm knot. As material around it thinned, jets may have burst from its poles, driven by magnetic fields threading the disk, carrying away angular momentum. The disk itself would have glowed in infrared and millimeter light, its temperature dropping with distance from the central object, its density setting the stage for different kinds of planets to form at different radii. Over time, winds from the young star and radiation pressure from its growing luminosity helped clear surrounding gas and dust. The dense envelope that once hid the protostar thinned, leaving a more exposed T Tauri-like star. Still variable, still contracting slowly, still surrounded by a disk, but now recognizably star-like. In that era, the sun would have been more active and magnetically noisy than it is today, casting out stronger winds that likely stripped lighter gases from the inner solar system and shaped the early atmospheres of the forming planets. When we say the sun is today about 4.6 billion years old, we are really dating the entire solar system. Using radioactive clocks in ancient meteorites that have cooled undisturbed since the earliest stages, those fragments tell a consistent story. The sun and its planets formed together, as part of the same collapse, at roughly the same cosmic moment. They also tell us something quieter, that the star you live under is not primordial. The universe had already existed for billions of years before this particular fusion engine began. The galaxy had already spun many times. The conditions that allowed this cloud to form and collapse were themselves the outcome of an earlier, longer history. Calling the newborn sun a luminous monster is not about malice. It is about scale and indifference. Even as a pre-main sequence object, its luminosity may have been tens or even around 100 times what it would settle into on the main sequence. Simply because its surface area was so large while it was still contracting, it dominated its immediate surroundings, carving a bubble in the molecular cloud, evaporating nearby gas, blasting the region with winds and radiation. This was not a gentle arrival. It was a violent assertion of gravity's success in one particular place. There is a strange intimacy in realizing that everything you know, every person, every story, every thought, unfolded in the aftermath of that collapse. The sun was not placed in the sky. It condensed out of a cold, dark cloud because, in that patch of the galaxy, density tipped over some threshold and gravity did what it always does. The fact that this led, eventually, to oceans, continents, nervous systems, and questions about meaning is not written anywhere in the equations. It is an emergent side effect of energy gradients and chemistry, explored over timescales that dwarf individual lives. If you picture the early solar system from far away, before planets finished forming, it would not look like a peaceful family of orbits. It would look like a bright young star, still somewhat bloated, surrounded by a dusty disk streaked with gaps and clumps where material was accreting into larger bodies. Collisions would have been frequent and catastrophic. Worlds half-formed and then shattered. Orbits perturbed. Fragments scattered and reassembled. What now feels like a clean arrangement of planets, spaced at reasonably comfortable distances from their star, began as a crowded, chaotic arena. Stability is a late development. In that arena, Earth's own beginnings unfolded. The material that would become this planet orbited in the inner, hotter part of the disk, where volatile compounds were less abundant and rocky material dominated. Over millions of years, countless impacts built up the planetesimals into a larger body. Later, a collision with another world-sized object likely gave rise to the Moon. A reminder that even finished planets carry scars from the era when the Sun and its retinue were still settling into their current configuration. Looking back at this from a human perspective, there is a temptation to imagine inevitability given a cloud, a collapse, a protostar. Of course, it leads to a stable star with habitable planets. The reality is more contingent. Many clouds never collapse. Many collapsing clumps fragment into multiple stars. Many young systems eject material violently, or end with planets in orbits hostile to complex chemistry. Even in our own system, small shifts in initial conditions could have produced a different arrangement of planets, or none in the region where liquid water is possible for long. What we can say with some confidence is that stars like the Sun are not rare. In the galaxy, there are billions of them, each the outcome of a similar sequence: cloud, collapse, protostar, disk, main sequence. The Sun is, in that sense, ordinary. It is an average star, with an average mass, born in an average kind of cloud, following the usual rules. The monster is not exceptional in the catalogue. The exception is the particular chain of consequences that, on one world, turned its steady output into forests, cities, and late-night thoughts about the nature of the star itself. When you step outside and feel sunlight on your skin, you are touching the endpoint of that long story, a photon that began as gravitational energy in a collapsing cloud, became thermal energy in a contracting protostar, turned into radiation from a fusing core, and finally, after a long diffusion outward and a short sprint through space, ended its journey in the molecules of your body. None of that journey was designed. None of it was about you, and yet you are here, able to trace the path backward, to imagine the cold cloud and the slow fall, to see the young star's violence not just as a hazard, but as a precondition for everything you care about. The luminous monster at the center of your sky did not mean to create you. It meant nothing at all. But in the narrow interval of time during which it burns steadily, under the particular arrangement of matter that happened to form around it, a small corner of the universe became aware enough to look up and ask where the light came from. The light that now seems so ordinary began as something else entirely, far from the calm surface, in a place where matter is squeezed so hard that even the rules about what can and cannot happen begin to bend. At the center of the Sun, in a region that reaches only to about 1/5 of its radius, lies the core, the engine that makes everything else possible. It is not a solid object, but a volume of plasma under conditions we cannot reproduce on Earth for more than brief moments. The temperature there is around 15 million Kelvin, hot enough that individual atoms no longer make sense as stable entities, and the density climbs to roughly 150,000 kilograms per cubic meter, more than an order of magnitude denser than solid iron. Pressure reaches values that, written out, look almost meaningless in human terms. Under those conditions, gravity wins its argument. Hydrogen is forced so close together that a different kind of physics takes over. Classically, protons should not fuse. They are both positively charged. Electrostatic repulsion should keep them apart unless they collide with energies far higher than even the core provides. If that were the whole story, the Sun would never have ignited. But at extremely small scales, particles are not just points, they are also waves, with finite probabilities of being found in places they are not allowed to reach. This is quantum tunneling, and it is the narrow path through which the Sun manages to shine. Protons in the core do not always need enough energy to climb over their mutual barrier. Sometimes, they appear on the other side. The dominant process is called the proton-proton chain. In its simplest outline, two protons fuse to form deuterium, releasing a positron and a neutrino. That deuterium then fuses with another proton to make helium-3, and pairs of helium-3 combine to form helium-4, with two protons left over to continue the cycle. At each step, a little mass is lost and reappears as energy. Comparing the total mass of 4 starting protons with the final helium nucleus, about 0.7% of the original mass is missing. That small fraction, multiplied by the constant that links mass and energy, becomes the luminosity of the Sun. Every second, roughly 600 million tons of hydrogen are processed in the core, with on the order of 4 million tons of that mass effectively converted into energy. Most of that energy emerges first as extremely energetic photons, gamma rays, and as kinetic energy of particles. A small fraction, a few percent, escapes immediately in the form of neutrinos. Those nearly massless particles that hardly interact with anything at all. They stream outward at almost the speed of light, barely noticing the rest of the Sun, and in a little over 8 minutes, they pass through Earth, through your body, and continue into deep space. Because the core is so dense, photons do not share that privilege. A gamma ray born in the very center cannot simply rush outward in a straight line. It is absorbed, re-emitted, scattered, deflected, changing direction innumerable times as it random walks outward through the radiative zone. Estimates suggest that the typical time for that energy to travel from the core to the base of the convection zone is on the order of hundreds of thousands of years. By the time it finally escapes from the photosphere as visible light, its original identity has been erased. The sunrise you see now began as core energy released long before any human beings existed. The core itself is compact. It contains about a third of the Sun's mass, but occupies only a few percent of its volume. And within that small fraction, about 99% of the fusion power is generated. Outside that sphere, temperature and density fall below the threshold where fusion can proceed efficiently. The rest of the Sun is not idle, but it is more like insulation and machinery, carrying energy outward rather than creating it. The raw, in physical terms, is concentrated in that central region where quantum tunneling keeps opening doors that classical physics would have sealed shut. From the outside, this sounds violent, and on some level it is. In each cubic meter of the very center, the power generation reaches hundreds of watts per cubic meter, comparable, remarkably, to the heat produced in a compost pile on Earth. The Sun does not shine because each small volume is wildly energetic. It shines because there are so many such volumes, all working at once, over an immense span of space and time. That mismatch between local mildness and global consequence is easy to miss. We are used to thinking that great effects require great intensity at every point. The core shows another route: modest processes, repeated in incomprehensible numbers, can shape everything. The fusion rate is not fixed. It depends steeply on temperature and density, so any small change in the core can, in principle, alter how much energy is produced. But the system is self-regulating. If fusion runs slightly faster, the extra energy raises the core temperature, increasing pressure and causing a minute expansion. That expansion lowers density and temperature just enough to reduce the fusion rate again. If fusion slows, the core cools and contracts, increasing temperature and density and nudging the rate back up. Over stellar timescales, the balance is not perfect. The Sun is slowly brightening as helium accumulates in the core, but on human timescales, this feedback keeps its output within a narrow band. There is something quietly unnerving in this stability. We like to think of balance as a gentle state, but the Sun's balance is an equilibrium between gravitational collapse and nuclear pressure, between a pull that would crush everything inward and a push generated by quantum processes that happen only because particles can sometimes be where they should not be. Your climate, your seasons, the viability of your biosphere, all lean on this compromise. It will hold for billions of years, but it is not eternal. As hydrogen is slowly consumed, The core composition changes. Gravity gains a slight advantage, and fusion must run hotter to compensate. The Sun today is already significantly brighter than it was when Earth first formed. Neutrinos are the most direct messengers from this hidden region. Because they barely interact, almost every neutrino created in the core flies straight out at nearly light speed, arriving at Earth without having bounced, scattered, or slowed for decades. Experiments measured fewer solar neutrinos than theory predicted, a discrepancy that became known as the solar neutrino problem. Only when physicists realized that neutrinos change flavor oscillating between different types as they travel did the numbers reconcile. This was not merely a technical correction. It was a moment when the Sun forced us to update fundamental particle physics. From an existential perspective, the core is a place where improbabilities are normalized. The initial step of the proton-proton chain, in which two protons fuse and one transforms into a neutron, is fantastically rare on a per-particle basis. For any given pair of protons in the core, the expected waiting time before they successfully fuse in this way can be longer than the age of the universe. Yet the Sun holds so many protons, packed so densely, that these vanishingly unlikely events happen constantly when counted across the whole core. The star exists because low-probability events, given enough trials, become certainty. It is difficult not to see a reflection there. Human lives are also built on chains of individually unlikely events, particular mutations, particular encounters, particular historical contingencies. We tend to retrospectively arrange them into stories of inevitability. The core refuses that comfort. It is a reminder that what seems stable and natural can be the long-term outcome of accidents repeating at scale, smoothed into a steady output only because we are looking from far away. There is another layer of unease in how the core's activities are separated in time from their consequences. The photons that began as gamma rays in those fusion reactions will not reach the surface for hundreds of thousands of years. The neutrinos pass through in minutes. The structural response of the star to gradual composition changes unfolds over billions of years. The processes that support your life are not aligned with your timescale. You are warmed by decisions made long before your species evolved. You are also living in a moment when those decisions still lead to tolerable conditions. That combination is temporary by definition. Yet within that temporary window, something curious happens. Matter that was once part of the cold molecular cloud which fed the Sun's core has been processed through this fusion engine and reorganized into planets, oceans, and organisms capable of understanding at least some of the story. The same core that steadily converts mass to energy also sets the conditions for carbon chemistry on a small world at a particular distance. Without quantum tunneling, without 0.7% of mass turning into light and heat, there would be no Sun as you know it. Without the long-term regularity of that process, there would be no opportunity for complex life to develop under its glow. The core does not know this. It does not know anything. It continues to fuse hydrogen into helium at a rate determined by density, temperature, and the deep rules of nuclear interaction. It will go on doing so until enough hydrogen is exhausted that the balance fails and the Sun begins to swell into a different kind of star. But the lack of intention does not make its role smaller. On the contrary, it sharpens the realization that meaning, if it exists anywhere, has to be made locally, by beings who emerge inside systems that are, at their base, indifferent. When you step into sunlight, you rarely think of the region, 20% of a solar radius from the center, where pressures and temperatures beyond human experience are quietly holding gravity at bay. You do not feel the quantum probabilities resolving themselves into fusion events. You do not sense the neutrinos passing through you in their trillions every second, carrying a tiny share of the core's energy away into the dark. What you feel is warmth. What you see is brightness. Behind that simplicity, at the heart of the Sun, a continuous, silent roar is underway, a roar made of improbable collisions and mass transformed, echoing outward across space and time until, much later, it becomes the ordinary light by which you read these words. The warmth that reaches your skin is the end of that roar. But almost nothing in that warmth tells you what the energy had to do to get there, or how long it has been traveling through the star before it ever touched open space. Imagine starting in the core, where hydrogen is being fused into helium, and choosing one packet of energy at the moment it is born. At that instant, it is not yet the soft yellow light you associate with morning. It is a gamma ray, a very high-energy photon trying to move outward through a medium so dense that, on average, it travels only about the length of a fingernail before it hits something, is absorbed, and is re-emitted in a new direction. This is where the sun's interior stops behaving like anything you have experienced. In empty space, a photon would cross astronomical distances in straight lines. In the radiative interior of the sun, it performs a random walk. Every tiny step is interrupted. After each scattering, it forgets where it was going and starts again. Taken together, these small amnesias mean that energy does not stream outward like a beam from a torch. It diffuses, slowly, as if lost in a bright fog. The region where this radiative diffusion dominates stretches from the inner core out to around 70% of the sun's radius, a zone in which photons carry energy by this repeated scattering rather than by the bulk motion of gas. Over that span, the temperature falls dramatically, from about 15 million Kelvin near the center to roughly 1.5 million Kelvin at the base of the convective zone. To us, those are just large numbers. To the photon, they are changing odds. With each step outward, the density drops a little, the mean free path grows, and the walk becomes less hopelessly confined. If you try to picture this walk in human terms, it helps to think of a person trying to leave a crowded stadium by taking only one small step before being turned in a random direction, over and over again. The straight-line distance to the exit might be modest, but the path actually taken will be a tangled scribble, revisiting the same regions many times. In the sun, the scale is worse. Calculations and models suggest that it takes on the order of hundreds of thousands to around 1 million years for energy released in the core to reach the surface as emerging photons. During that time, the individual photons are not preserved as identifiable travelers. Each absorption and re-emission resets the story. Energetic gamma rays gradually become X-rays, then extreme ultraviolet, then lower energy forms. By the time energy approaches the outer layers, it is no longer a single, ancient photon struggling outward, but a population of much softer photons whose collective energy can finally escape. The journey is less a heroic quest and more a statistical migration, energy losing memory of its origins as it is shared again and again with the surrounding plasma. There is a kind of quiet philosophy in that. We like tales of straight causes and effect, of clear lines between action and result. The sun does not work that way. The light that falls on your hand is not a direct message from a single event in the core. It is the end state of an enormous, tangled process whose individual steps are forgettable and whose outcome is steady only when you average across immense numbers of interactions and immense spans of time. At some point on the way outward, conditions change enough that this diffusive transport becomes inefficient compared with a different process. Near that level, the temperature has dropped to a few million Kelvin and the material has become more opaque to radiation. Here, instead of photons making most of the progress, bulk motions of gas take over. This is the base of the convective zone, the outer roughly 30% of the sun by radius. In this convective region, hot plasma rises, cools as it radiates, and sinks again, carrying energy upward, more like boiling water than shining metal. The path of energy becomes more coherent at larger scales, but no less chaotic in detail. Towering convection cells churn, merge, and fragment, transporting heat in swirling three-dimensional flows. Compared to the long stagnation in the radiative zone, this leg of the journey is fast. Material can cross the convective layer in times closer to days and weeks than to millennia, though it does so in loops, not straight paths. Eventually, those rising currents reach the photosphere, the thin layer only a few hundred kilometers thick, where the gas finally becomes transparent enough that photons, once emitted, can travel freely into space. That boundary is not a sharp wall so much as a change in probability. Just below it, a photon's chances of being scattered again are still high. Just above it, the chances fall enough that most photons will make it out. When we say that light leaves the sun at this surface, we are really saying that the average photon has crossed a threshold in escape likelihood. Once free of the sun's atmosphere, the difference is immediate. The random walk stops. The photon enters almost empty space, where particles are so scarce that it can travel for years without hitting anything. Its speed, constant and fixed by the structure of space-time itself, is about 300,000 kilometers per second. Now the journey has a clear geometry. From the Sun to Earth is about 1 astronomical unit, roughly 150 million kilometers on average. And at that speed, the trip takes about 8 minutes and a little more than 20 seconds. This is the part of the story we usually tell. Sunlight takes a bit more than 8 minutes to reach us. It sounds straightforward, almost modest, especially compared to the hundreds of thousands of years spent wandering inside the star. Yet even here, the simplicity is deceptive, because Earth's orbit is not a perfect circle. That travel time changes slightly over the year, because light cannot go any faster. Every glance at the sun shows you the star as it was those minutes ago, never quite in the present. The gap is small at human scale, but it is there. A reminder that even the nearest star is always a little in your past. On its way, the photon passes other possible destinations. Some will skim past Mercury and Venus. Some will continue outward past Mars and the outer planets. Some will miss every world entirely and head into the interstellar dark. There is no preference in the emission. The sun radiates in all directions. The fact that a tiny fraction of those photons intersect a small rocky planet at just the right distance to sustain liquid water is a geometric coincidence layered atop the longer story of stellar and planetary formation. When a photon finally reaches Earth, its story is still not quite finished. Many are intercepted by the upper atmosphere, scattered by molecules and tiny particles. Shorter wavelength photons scatter more strongly, which is why the daytime sky appears blue and why the sun looks reddened at sunrise and sunset, when its light passes through a thicker slice of air. Some photons are absorbed and re-emitted, some lost to heating the air, some redirected toward the ground as diffuse skylight. Only a fraction of the original beam makes a relatively straight path down to the surface. Those that do arrive meet different fates. A photon might strike the surface of the ocean, be absorbed in the top layer of water, and contribute a microscopic amount of heat that helps drive currents. It might hit a leaf, where pigment molecules in a chloroplast use its energy to kick an electron into a higher state, starting a chain of reactions that store part of that energy in chemical bonds. It might enter your eye, be absorbed by a photoreceptor cell in the retina, and trigger a cascade that your brain interprets as brightness, as color, as the edges of objects in the world. By then, the photon's identity as something that came from the sun is purely historical. Its energy has been redistributed yet again. This time inside an atmosphere and inside a living organism. You carry the trace of those journeys in the warmth of your skin after a day outside, in the chemical energy of the food you eat, in the electrical activity of your nervous system. There is no clear line between the sun's output and the internal landscape of your own body. The distinction exists mostly in language. If you pull back and look at this entire chain from the quantum tunneling in the core that allows fusion to occur, through the long, random walk of radiative diffusion, the turbulent climb through convective layers, the brief free flight across interplanetary space, and the final absorption in air, water, or tissue, it becomes difficult to maintain any sense that sunlight is simple. The beam that feels so direct on your face is the outcome of processes that span timescales, from nuclear to geological to human. It is also, in a sense, fragile. The diffusion time in the interior depends on the density and opacity of the sun's material. The structure of the radiative zone and convective zone depends on gradients of temperature and composition. The exact brightness and spectrum of the light that arrives at Earth's orbit depends on the star's current age, its core temperature, and the slow changes in its output over billions of years. You live in a moment when those parameters happen to combine in a way that allows complex ecosystems and technological societies. That moment is long on a human timeline and short on a stellar one. At the same time, the details of any single photon's path do not matter to the sun. The star does not track which packets of energy will end up in a glacier, a leaf, a solar panel, or a human eye. It does not distinguish between photons that will warm bare rock and photons that will become part of a thought about the nature of photons. The difference exists only at the receiving end, in the systems that have evolved or been built to use that energy in particular ways. When you watch light move across a room over the course of a day, you are watching the final centimeters of a journey whose earlier stages were so slow and so tangled that your entire species' history fits comfortably inside them. Photons that began their interior walk while no vertebrate life existed on land are only now emerging at the photosphere and beginning their 8-minute sprint toward someone's window. Others, created more recently, are leaving now and will still be bouncing around inside the sun's outer layers long after your civilization has changed beyond recognition. The next time light falls on your hand, it is still just warmth. It is still just illumination. Nothing in that sensation will tell you whether the energy has waited hundreds of thousands of years inside the star or only a little less. Whether its last scatter happened under a quiet patch of photosphere or near the root of a magnetic structure. But if you hold the thought that this is the end of a journey through density, randomness, and distance, the ordinary moment sharpens slightly. You are not just standing in sunlight, you are standing in the final, a fleeting phase of a process that began deep in a place you can never visit, and that, for almost all of its history, did not know you were going to be here to feel it. The process that brings that light to you is not as steady as it feels. Underneath the apparent constancy of daylight, the star's own machinery is breathing in cycles, quietly tightening and loosening the conditions you take for granted. If you could watch the sun not over a day or a year, but over centuries, speeding time up until human history ran past like weather, you would see a pattern emerge. The face of the star would not keep the same level of agitation. Dark sunspots would appear in small numbers, then multiply, spread into complex groups, and finally fade again. Bright magnetic regions would bloom and then recede. On average, this rise and fall repeats roughly every 11 years, a rhythm known as the solar cycle. Beneath that, the underlying magnetic field flips polarity and returns to its original configuration over about 22 years, a longer oscillation called the Hale cycle. The sun's heart, in other words, beats in magnetism. The mechanism behind this pulse is a dynamo, but not in the familiar sense of a device you could build on a bench. It arises from the combination of hot plasma, rotation, and convection in the sun's interior. The star does not rotate as a solid body. Near the equator, the surface takes about 25 days to complete one turn relative to distant stars, while near the poles, it takes closer to 35 days. That differential rotation stretches and winds magnetic field lines around the star, amplifying them and tangling them. Deeper down, at the interface between the radiative interior and the convective envelope, shear flows and turbulence twist those fields into more complex shapes. Over time, this churning stores magnetic energy in the sun's outer layers. When conditions are right, concentrated fields rise buoyantly through the convective zone and punch through the photosphere in pairs of opposite polarity. Where they emerge, convection is suppressed and the surface cools, forming sunspots. In periods of low activity, only a few such regions decorate the disk, sometimes none at all. In periods of high activity, more than 100 spots and groups can be visible at once, scattered across mid-latitudes in patterns that drift toward the equator as the cycle advances. From Earth, these changes look minor. The sun remains roughly the same color and brightness. To resolve the spots, you need filters and magnification. Yet, the difference between a quiet sun and an active one is not cosmetic. Along with sunspots come enhanced ultraviolet and X-ray emission, more frequent solar flares, and more coronal mass ejections. The invisible environment through which Earth moves becomes more turbulent. Space near our planet fills with additional energetic particles and shifting magnetic structures, even while the daylight itself feels unchanged on your skin. The total solar irradiance, the overall power per unit area received at the top of Earth's atmosphere, varies surprisingly little over the cycle. Measurements from satellites show that between activity minimum and maximum, it changes by about 1/10%. Less than 1 part in 1,000. The smallness of that number is deceptive. In certain bands of ultraviolet radiation, the variation can be several percent or more, enough to affect the chemistry and temperature structure of the upper atmosphere. What looks to us like a nearly constant lamp is, at specific wavelengths and heights, a shifting source. This regular irregularity leaves scars in data far removed from solar telescopes. Records of radio communication, satellite failures, and even the frequency of auroras track the solar cycle's peaks and troughs. Tree rings and ice cores preserve subtle imprints of long-term changes in cosmic ray flux, which are modulated by the sun's magnetic field and wind. When the sun's activity is high, its extended magnetic bubble, the heliosphere, shields Earth more effectively from galactic cosmic rays, reducing their penetration into the atmosphere. When activity is low, more of those particles reach our planet. The star's heartbeat reaches down even into the chemistry of air and the slow growth of wood. What is unsettling is how this pulse intersects with our sense of stability. On human timescales, 11 years feels like a middle distance, longer than an election cycle, shorter than a career, about the length of a childhood phase. Many of us mentally file it under almost permanent. Yet for the sun, that period arises from the interplay of flows and fields in zones so deep that we cannot yet map them in full detail. The precise length and strength of each cycle are not perfectly predictable. Some cycles are strong, crowded with spots and storms. Others are weak and quiet, occasionally, over centuries. There are extended lulls, times like the Maunder minimum when sunspots nearly vanish for decades. The star's heart does not always beat on schedule. When that heartbeat quickens, Earth's magnetic environment contracts and shudders more often. Geomagnetic storms become more frequent. High-latitude skies glow with auroras more regularly. Radiation conditions in near-Earth space shift in ways that matter to satellites and astronauts. Airline routes over polar regions adjust to avoid increased exposure during strong events. Even electrical grids on the ground feel the difference. As geomagnetically induced currents become more likely to creep along long wires and into transformers, none of these effects are constant. They rise and fall with the sun's internal clock. From another angle, the 11-year cycle is a form of memory. The sun remembers. in its fields and flows, what it has done in the recent past. Magnetic structures built during one cycle set the initial conditions for the next. The reversal of polarity at each maximum means that the star's large-scale magnetic field knows, in a physical sense, which phase of the 22-year Hale cycle it inhabits. We still do not fully understand all the details of this solar memory. Competing models link the cycle to meridional flows that carry magnetic flux toward the poles and back toward the equator, to turbulent pumping within the convection zone, to subtle instabilities at the tachocline where rotation profiles change. The fact that such a basic piece of the Sun's behavior remains imperfectly understood is its own kind of warning against overconfidence. It is easy, living through only a handful of solar cycles, to treat this rhythm as permanent. But nothing in stellar evolution guarantees it will always be present in its current form, on much longer timescales. As the Sun ages and its internal structure gradually shifts, the character of its dynamo may change. Observations of other stars show a range of behaviors. Some rotate faster and have shorter, more intense cycles. Others rotate slower and appear magnetically quieter, perhaps in states where cycles are weak or irregular. Our star is one case in a wide family of possibilities. Its unstable heart is, for now, stable enough to support the kind of world we know. That, for now, stretches far beyond any human lifetime and still falls short of forever. There is a human pattern that echoes this. We often build our lives around things that seem regular: seasons, paydays, school years, the turning of calendars. We plan as if the underlying systems will remain within familiar bounds. The solar cycle sits beneath many of those patterns, invisible but real, altering the environment in which our technologies operate and in which our atmosphere slowly breathes. You rarely notice it directly. It is background to the background, a slow pulse in the thing you already treat as fixed. If you were to live long enough to watch 10 or 20 cycles unfold, the Sun's behavior might start to feel more like weather, sometimes stormy, sometimes calm, sometimes oddly quiet for longer than usual. You would see that its activity is not a straight line but a wave, that its apparent stability is a band rather than a point. From there, it is only a small step to realizing that many of the certainties we rely on have the same character. They are not guarantees. They are intervals in which fluctuations remain small enough for our plans to survive. The Sun's 11-year pulse is not a story about impending disaster. It is a story about living next to a system that is, by its nature, dynamic and only approximately predictable. The light will almost certainly keep arriving each morning throughout your life. But wrapped around that light is a magnetic cycle that occasionally sharpens, flares, and brushes more harshly against the technological shell we have built around our planet. Understanding that pulse does not make the star safer or more dangerous. It does something subtler. It adjusts where you place your sense of security. Instead of imagining the Sun as a perfectly steady lamp hung in an unchanging sky, you begin to see it as a rotating, convecting, magnetized sphere whose inner flows generate cycles, whose cycles generate storms, and whose storms sometimes reach across space to touch the systems you depend on. The heart that sustains your daylight is, and always has been, a little unstable. The instability would be easy to ignore if it stayed abstract. If magnetic fields only twisted and snapped in the emptiness around the Sun, it becomes harder to look away when that motion threads itself through the thin shell of space that your entire civilization actually occupies. Most of the time, the journey from Sun to Earth feels uneventful. Photons make their 8-minute sprint. The solar wind washes past in its usual streams, and the magnetosphere quietly shapes and deflects what it can. But every so often, the silent explosions higher up in the corona launch something more structured, more concentrated, a coronal mass ejection with just the right timing and direction to collide with Earth's magnetic field. When that happens, The star's roar stops being a metaphor and becomes a pattern of currents and fields flowing through the space you live in. Earth is not defenseless. The planet's molten outer core generates a global magnetic field that extends tens of thousands of kilometers into space, forming a cavity in the solar wind called the magnetosphere. On the day side, facing the sun, this magnetic bubble is compressed by the solar wind to a distance of roughly 10 Earth radii. On the night side, it is stretched into a long magnetotail that can reach beyond 200 Earth radii downstream. This structure does not block particles like a wall, it guides and redirects them, forcing charged particles to follow curved paths along field lines rather than flying straight inward. When a coronal mass ejection arrives, it does not simply bounce off this field. The ejection carries its own magnetic structure, and when that embedded field is oriented opposite to Earth's, magnetic reconnection can occur at the boundary. In those moments, part of the Sun's field effectively merges with Earth's, opening channels through which energy and particles can flow into the magnetosphere. The day side is squeezed harder, the magnetotail is stretched further, and currents begin to surge along newly connected field lines. The result is what we call a geomagnetic storm. To instruments in orbit, the change is obvious. Satellites see sudden increases in energetic particle flux. Magnetometers register rapid fluctuations in the local field. Auroral cameras record curtains of light brightening and expanding toward lower latitudes. To someone on the ground, the effects are more indirect. High-frequency radio signals can fade or be absorbed. GPS accuracy can degrade as the ionosphere becomes disturbed. In extreme cases, currents induced in long conductors on the surface can overload transformers and knock out sections of electrical grid. The Carrington event of the 19th century remains the most famous example of what happens when the roar really does reach Earth. In late northern summer of that year, an exceptionally bright solar flare was observed by Richard Carrington and Richard Hodgson. Within about a day and a half, the associated disturbance hit Earth with unusual force. Auroras were seen as far south as the Caribbean, and telegraph operators reported sparks leaping from their equipment, papers catching fire, and systems working even when disconnected from their power supplies because geomagnetically induced currents were sufficient to drive them. At the time, the global electrical infrastructure was sparse, essentially long wires and crude instruments. The storm still managed to set parts of it on fire. Modern analyses estimate that the magnetic disturbance associated with the Carrington storm was on the order of several times stronger than typical strong geomagnetic storms measured in the space age. Reconstructed values of the disturbance storm time index suggest an event more intense than anything recorded by direct instrumentation since. In the centuries before and after, ice core and tree ring records hint at other large solar particle events. Their signatures written in spikes of certain isotopes the Sun has, on occasion, sent streams of particles and fields far beyond the usual background. Today, the landscape of vulnerability is different. Instead of a world linked by relatively simple telegraph lines, you live in a civilization whose nervous system is built from dense, fragile networks, satellite constellations in multiple orbital shells, high-voltage transmission lines connecting power stations and cities across continents, submarine cables carrying data under oceans, navigation systems that assume a quiet ionosphere. None of these systems were designed with a perfect understanding of what a truly extreme solar storm might do to them. Because such storms are rare on human timescales, and because our most complex infrastructures are younger than a single human lifetime, even moderate space weather events remind engineers of the connection. In the late 20th century, a storm associated with a strong coronal mass ejection caused currents in the ground beneath parts of North America, overloading transformers and leading to a province-scale blackout that lasted several hours. Satellites have been lost or degraded during periods of heightened activity. their electronics damaged by energetic particles, or their orbits altered by increased atmospheric drag as the upper atmosphere heated and expanded. These incidents are not science fiction glimpses of some future disaster. They are the early warning, demonstrations that the solar environment is already entangled with daily life. If you live far from polar regions, it is easy to think of auroras as rare and distant. During strong storms, that boundary shifts. Curtains of light that usually dance near the poles can creep equatorward, appearing over cities that do not often see them. To human eyes, the display is beautiful. Rippling sheets, arcs, and spirals of green, red, and violet light tracing magnetic field lines in the sky. Physically, those shapes are the visible edge of energetic particles funneled along Earth's field, colliding with atoms and molecules in the upper atmosphere and making them glow. The same processes that fuel that beauty are also depositing energy high above your head, altering densities, currents, and chemistries in layers of air you will never directly experience. There is a quiet tension in this duality. We are drawn to the spectacle of the storm while living inside systems that can be quietly pushed toward failure by the same forces. That is often how contact with larger scales feels. A sunrise is both aesthetic and structural, a color gradient in the sky and a change in energy balance at the surface. A geomagnetic storm is both a light show and a stress test for technologies whose smooth functioning we mistake for normality itself. From a more personal perspective, the idea that space weather can black out cities or scramble navigation might seem unsettling in a way that earthquakes or hurricanes do not. Geological and atmospheric disasters are local. They have boundaries you can draw on maps. Solar storms are more diffuse and indifferent. They do not aim for particular countries or follow coastlines. When the roar reaches Earth, it does so at planetary scale, modulated by latitude and magnetic geometry, rather than by borders or histories. Your particular grid, your particular satellite, is affected only because it happens to be there, wired into a field that is being briefly reshaped by forces originating 93 million miles away. None of this implies doom as an inevitable outcome. The same physics that creates the risk also makes prediction possible. Space agencies and meteorological services now monitor the sun continuously with fleets of spacecraft. Instruments parked between Earth and Sun can detect changes in the solar wind tens of minutes before they reach the magnetosphere, providing at least short-term warning. Coronagraphs can image coronal mass ejections leaving the Sun, allowing forecasts of their arrival times and likely impact strengths days in advance. Models, imperfect but improving, simulate how magnetic structures might interact with Earth's field. Those forecasts buy time, hours to configure grids into safer modes, to postpone certain satellite operations, to adjust aircraft routes, to prepare systems for potential disruptions. They do not remove the underlying dependence. The planet still orbits the same star, and the star still produces storms. But the ability to see those storms coming, to treat them as part of the environment rather than as unannounced acts of fate, shifts the relationship slightly. The roar remains beyond your control, your response to it does not. There is an echo here of the broader theme that runs through every contact with the sun. The star does not need you. It did not burn for your sake and will not change its behavior to accommodate your preferences. Yet within the margins, it leaves within the quiet average. Between its storms and lulls, life and civilization have found niches. The same light that can, in rare bursts, threaten your machines is the light that, at lower intensity, built the biosphere those machines rely on. The same magnetic complexities that throw mass into space are part of the dynamo that has kept the sun's output within a range suitable for liquid water on a small rocky world. Living with that contradiction is unavoidable. You are sustained by something that cannot be made safe in any final sense. Only understood, monitored, and adapted to. The idea that safety might someday be complete with perfect prediction, perfect shielding, perfect control is another kind of illusion. Comforting but misplaced, the more honest picture is one of ongoing negotiation, a technological species learning how to operate inside a variable stellar environment, aware that the background conditions are not fixed, aware that its own systems add layers of fragility. On clear nights at high latitudes, when the sky is bright with aurora, people still go outside and look up. They wrap themselves against the cold and watch the sky move. Aware, perhaps, that somewhere, engineers are watching graphs, that some instruments are registering elevated particle counts, that there may be more noise in some communication channels. Most of those viewers are not thinking of magnetohydrodynamics or coronal mass ejections. They are thinking of beauty, of strangeness, of feeling small, and they are right to. The spectacle is not less real because the physics can be described. But knowing the physics changes the feeling. It adds an extra layer of clarity to the smallness. Those pale green curtains and sudden crimson arcs are manifestations of a star's shifting magnetic field, reaching across space to shake a planet's protective bubble. The glow is not directed at you. It is simply what happens when charged particles follow field lines into thinner air and find atoms to excite. You are watching the interface between a local life support system and a distant, indifferent engine. The roar that reaches Earth is not an exception to the sun's nature. It is one of its normal voices. Most of the time, it speaks softly enough that you can forget it is there, wrapped beneath the steady impression of daylight. Occasionally, it raises its volume, and currents surge through sky and ground alike. Your species has built a world that is sensitive to those surges, and that sensitivity is both a vulnerability and a sign of how much you have learned to use the same energy that threatens you. To step outside on a quiet day is to stand inside the average between storms, in a temporary lull that happens to be long enough, gentle enough, for plans and cities and languages to accumulate. To understand that this lull is not an entitlement, but an interval in a louder, older process, is to see your situation more clearly. You are not just under a blue sky, you are sitting inside the thin, shifting sheath of a magnetic field, orbiting a variable star, listening, whether you notice it or not, for the next time its silent roar brushes against your world. The same field that flexes around your planet also reaches into you in quieter ways, not as a storm in the sky, but as patterns of light and dark that slowly carve themselves into your biology. Your body does not experience the sun as an abstract star. It meets it as a rhythm. Long before you knew what a solar cycle was, you were already being trained by a simpler one, the alternation of day and night. Inside your brain, in a cluster of cells deep in the hypothalamus, sits a tiny timekeeper that tracks this alternation using light that reaches the back of your eyes. When morning light hits specialized cells in the retina, they send signals that reset this internal clock, telling your physiology where it is in the 24-hour cycle. Hormones rise and fall. Body temperature drifts. Digestion speeds up or slows, all in response to this daily conversation with the sky. You can feel that dialogue when it is interrupted. Travel quickly across time zones, and the mismatch between your inner clock and the new pattern of light leaves you disoriented. Awake at the wrong hours, hungry at odd times, spend long periods in windowless rooms, or in artificial light that never quite imitates the changing spectrum of the sun. And sleep can become shallow or irregular. Your insistence that you are a separate, self-contained mind collides with the fact that your basic rhythms are entrained by photons from a distant nuclear furnace. You are not just living under the day, you are carried along by it, whether you agree or not. Mood follows that rhythm too, in ways that can be gentle or brutal. For many people, long stretches of low daylight in winter bring with them a heaviness that is not entirely psychological. The amount and timing of light on the retina influence the balance of neurotransmitters involved in wakefulness and mood. Step outside into bright midday sun after days of gray, and the change in how you feel is not an illusion. It is the nervous system responding to a different input stream, adjusting the chemistry that underpins your sense of self. The sun does not care how you feel. It rises with the same indifference regardless, but your internal world is still dragged along behind its apparent motion. On evolutionary timescales, this dependence goes deeper. Life on Earth emerged and diversified under a sky that turned from dark to bright and back again with solid reliability. Cells evolved molecular clocks that anticipate dawn and dusk. Plants open and close their leaves. Animals adjust their activity to match hunting opportunities and predator risks. Migratory species time their journeys to changing day length. Reproductive cycles in many organisms are tuned to seasons, which are themselves a pattern written by the tilt of Earth's axis and the way sunlight is distributed over its surface. Humans, with electric light and climate control, sometimes imagine they have stepped outside of this pattern. Yet our earliest calendars were attempts to track the sun's apparent path, to predict solstices and equinoxes, to anchor rituals in the turning of the year. Agriculture needed those predictions to decide when to plant and harvest. Culture borrowed them to decide when to celebrate, mourn, or begin again. Even now, buried inside modern holidays and fiscal years and school terms, there are faint outlines of older solar rhythms. The star's motion was not just a source of energy, it became a scaffold for meaning. Solar variability nudges the environment in subtler ways. Over decades and centuries, small changes in solar output and in the structure of the solar wind influence the balance of energy arriving at Earth's atmosphere. They interact with volcanic eruptions, ocean currents, and greenhouse gases to produce climate patterns that are only partly predictable. There have been periods when reduced solar activity coincided with cooler conditions, with rivers freezing more frequently and growing seasons shifting. For people living through those times, the causes were invisible. They saw only the effects, harvests failing more often, winters feeling longer, familiar patterns no longer lining up with inherited expectations. This does not mean that your moods or histories are written directly by the 11-year cycle or by small variations in ultraviolet flux. The chain of causality from solar surface to human mind is too long and too tangled for simple claims. But the fact that light and magnetism from the sun can, through layers of atmosphere, climate, ecology, and physiology, reach into the timing of your sleep, the stability of your mood, and the shape of your societies is enough. The roar does not have to be loud to matter. It can be almost silent and still rearrange the background conditions under which you decide who you are. There are even traces of the sun inside you that you cannot feel at all. Neutrinos created in the core pass through your body in unimaginable numbers every second, hardly ever interacting. Ghost-like. They carry with them information about fusion processes that began moments ago at the center of the star. You never notice them. They do not change your cells in any obvious way. Yet they are a continuous reminder that the boundary of your body is porous at the smallest scales, that particles from a distant region you will never visit are passing through you all the time. More mundane, but more consequential, is the way solar energy is folded into your own metabolism. The food you eat is, in almost every case, sunlight translated into chemistry. Plants use photons to build sugars from carbon dioxide and water. Animals eat those plants or other animals that have eaten them. You eat all of it. The energy that powers your muscles, that maintains the tiny voltage across your neurons, that supports the activity you recognize as thought, began as photons absorbed by chlorophyll somewhere. Sometime. The same core that fuses hydrogen into helium is, many steps later, responsible for the fact that you can lift a hand or form a sentence. It is easy to say that, and just as easy to slide past what it implies. We tend to imagine the self as something hovering above or behind the body, making use of it as a tool. In reality, what you call you is a particular organization of matter and energy, held together temporarily by flows that have their source outside you. Turn off the supply of sunlight for long enough, and those flows stop. The structures they maintained decay. The sense of being a continuous, independent observer dissolves. Not because anything spiritual has been refuted, but because the physical support for that experience has been withdrawn. This can sound bleak, but it has another side. If your thoughts are, in some sense, slowed and structured sunlight, then the questions you ask about meaning, purpose, and value are themselves products of stellar processes. The universe does not announce their importance. The sun does not adjust its brightness in acknowledgement. Yet, in one small region under its light, energy that began as blind fusion has become capable of reflecting on that fact. The roaring, indifferent star has, without intention, given rise to beings who can hear a trace of that roar within their own patterns of feeling and thought. On some level, you carry the sun's history in your body. The atoms that make you were forged in earlier stars, dispersed, gathered into the cloud that collapsed to form this one, sorted into planets, woven into cells. The timing of your days is set by the turning of Earth under the sun's light. The warmth in your blood is partially inherited from photons that left the photosphere minutes ago. The chemical energy in your brain was assembled from sugars built in leaves that unfolded in past seasons under the same sky. You are not outside the system. You are one of its temporary configurations. Knowing this does not tell you what to do with your life. It does not answer questions about right and wrong, about love, about loss, about what it means to be a good person in a complicated world. Those questions arise at a scale where physics becomes context rather than script. But the knowledge does relocate you. It strips away the comforting idea that you live in a world built for you and replaces it with something starker and in paradigm. Perhaps more honest. You live in a narrow, temporary corridor of conditions carved out by a star that does not know you exist. Within that corridor, there is still room for everything human. There is room for joy, grief, curiosity, cruelty, kindness, boredom, transcendence. There is room to build instruments that watch the sun and models that predict its storms. There is room to write stories about the sky and songs about light. There is even room to forget, most days, that any of this rests on a structure of nuclear reactions and radiative diffusion and magnetic cycles. The fact that you can forget is itself a side effect of how generous the current conditions are. The unheard roar within you is not a sound. It is the sum of these quiet dependencies, the ticking of internal clocks tuned to daylight, the firing of neurons powered by ancient photons, the chemical dances that only make sense at certain temperatures and under certain spectra of light. You do not sense it directly. You feel only the surface, a mood, an impulse to sleep, a burst of energy in afternoon sun, a restlessness in long winter dark. Beneath that surface, the workings of a distant star are still unfolding, translated into the ordinary texture of being alive. There is a moment, standing in sunlight, when you can feel both truths at once, that this warmth is the most ordinary thing in your life, and that it is the most precarious. The sun does not know that you are here. It does not know that there is a narrow strip of rock at just the right distance, where oceans can stay liquid, where chemistry can knit itself into cells, where those cells can learn to regret, to hope, to remember. The star makes no promise to keep that strip habitable. It only continues the reactions in its core, the flows in its plasma, the slow brightening written into its evolution. You, on the other hand, know. You know that every breath you take is made possible by a balance you did not choose and cannot maintain. You know that the same light that feeds forests could under different conditions. Strip away atmospheres or boil seas. You know that your entire history fits into a thin, quiet slice of a star's lifetime, and that there will be a time before and a time after when nothing like you exists here. That knowledge can feel cruel. It cuts against the instinct to believe that the universe must care, that the rising of the sun each morning is in some way an answer to human need. But it also does something more honest. It returns the responsibility for meaning to where it has always actually lived, not in the sky, but in the choices made under it. If the sun is indifferent, then every act of kindness, every refusal of cruelty, every attempt to understand, exists without cosmic endorsement. It is not guaranteed, not scripted, not backed by anything larger than the fragile network of minds that decide to keep doing those things anyway. In a world lit by an uncaring star, decency is not automatic. That is precisely why it matters. You will never hear the sun's roar. Space will always steal its sound. What reaches you instead is a silence filled with light, and a question it will never ask out loud, knowing how contingent this all is, this climate, this biosphere, this brief human era. What will you do with the mornings you are given? One day, the roar will outlast you, your species, everything you built. Today, it arrives as a sunrise. That is not comfort. It is an invitation to live as if you understood where the light really comes from, and how little time you truly have beneath it.